Ladies and gentlemen, I want to say a big welcome to all of you to the Valley of the Shadows of Management Science. Everything you've been doing up to now, everything is deterministic. Where you know that you are going to get an X value and you go for it and you actually get an X value is deterministic. Everything that you do is certain. But there are certain things in life that are not certain, and such models are known as probabilistic. Probabilistic models are models that are not clear, it's not certain. And that leads us to what is known as probability. Who can give me another word for probability? Just give me another word. Just another word for probability. Type it there, raise your hand, speak out. What is another word for probability? Type it there. Engage yourself more in the class. Type it in the chat or raise your hand and comment. What is another word for probability? Chance. Paul says chance. Chance. Someone has said chance. Bring another word aside chance. Apart from chance. Today's work we are doing requires you to pay attention more than ever. I beg you. If you don't get it, it's because you are not paying attention. I will beg of you to focus all your attention on what we are doing. Focus. Focus, I beg you. Okay, likelihood. A likelihood of something happening, that is a probability. Okay. Why do we study it? Because the thing is that the sample you are collecting and making judgment always might be wrong. What do you think? Will the NDC win the next election or the MPP will win the next election? Whatever answer you gave me was out of your feeling. You must gather data. You must collect a sample. The sample you collect will determine whether the conclusion you make is right or wrong. Why do you think that even though the Democrats were so positive that they were going to win, the Republicans swept most of the electoral votes? What were the chances? That was evident. What was the sample size? You see, we always make conclusion. What do you think is going to happen tomorrow? Will it rain or will it not rain? What is the likelihood that you are going to become a millionaire next year or not? What shows that you will do your master's and you will get a wonderful grade? What is the probability that you will ever become a doctor or you will never become? How do you know you will die tomorrow or you will not die tomorrow? Probabilities exist. Uncertainties exist. And because uncertainties exist, you got to be certain. And one way you can do certainty analysis is doing probability analysis. That's why we study probability. Now, what is probability? It's a likelihood of an event happening. Now, remember, before you can say that an event can or will happen, you must have taken a longer time and looked at its long-run relative frequency. It is a long-run relative frequency that will help you. So before you can do that, you must have an experiment. Any experiment is any situation where the outcome is uncertain. For example, if I pick a card from a deck of cards, I'm not clear whether I'll pick a jack, I'll pick a diamond, I'll pick a spade, a queen, or king. It's not clear. It's not clear at all whether I'll pick any of these. Now, if you leave tomorrow, right now, look at the situation. You are in a certain event right now. The event is called lecture. This is an event which is happening. There is another event that you could have been doing right now, attending a funeral or doing a wedding or watching a football match. It is uncertain the outcome of that event. Some of them will be certain, some of them will be uncertain. So when you have an experiment or an event, the highest certainty is 1. The lowest certainty is 0. And that lowest certainty is said to be uncertainty. So when you are not certain at all, it is 0. When you are fully certain, is 1. So probability is in between full uncertainty and full certainty. That's probability. Let me give you a typical simple example you know already. Then it will give you a better understanding of what probability is. Let's take an event of rolling a die. You normally roll the die. Now, the people that normally roll the die, what number are they usually expecting? Most of the time. What number are they usually expecting? What number? 6. Ebenezer, correct. So they're expecting the number 6. Now, if you roll the die, okay, there are possibilities of 6 situations. Either you get a 1 or 2 or 3 or 4 or 5 or 6. What is the probability that you will get a 6? Who can tell me? What is the probability that this roll you get a 6? What are the chances? What's the probability? What's the chance? It's 1/6. Now that 1/6, you got that 1/6.
1/6.
What does that mean? What does that 1/6 mean? What it means is that you have a certain percentage, because you can convert that 1/6 into a percentage. That 1/6 is how close certain you are to getting that 6. Now, what is the probability of you not getting a 6, but you rather getting an even number? You can tell us. What is the probability of getting an even number if you roll a die?
1/2.
That is half. Okay, because an even number is 2, 4, and 6, which is 3 numbers out of the 6. That word out of the 6 is the sample size. What is the probability of getting an odd number? What is the probability of getting an odd number? Be careful.
1/2.
By the way, she's answering the answers, blah, 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 blah. Okay, that's really good. Okay? I like that. So that is half. Let's take a classical probability. I'm going to go to a classical probability situation before I come to an actual probability situation. Okay, classical. The dean of the University of Ghana Business School has looked at 3,000 students' records. They received certain grades in management science over the past 4 years. The dean has asked the secretary to find out, develop some information. But what they want to do is that they want to know the number of students who had made grade of A, B, C, or D. This is your data. The number of students that made A were 300 out of the total. The number of students that made C were 1,005 out of the total. And those that made F are 150 out of the total. Question. Simple probability. So question. What is the probability that if I pick a student, that student had an A? You can tell me. What is the probability that if I select a student at random, that student had an A? This is called marginal probability. It's like, you got to know that probability is a ratio. Probability is also a percentage. That is 300 over 3,000. Very good, Osman. So it's 10%, 0.1. Okay. You have to first of all know the total. So the probability that a student gets an A is going to be that 300 over the total of 3,000, which is 10% or 0.1. What is the probability that if I select a student at random, that student had an F? Who can tell us? You're looking at simple probabilities, marginal. That student had an F. What's the probability? Type it there. say there, 0.5, 0.05, okay? Because the student to have an edge is 150 over the 3,000, and that is 0.05. If I pick a student at random, what is the probability that the student had either I was going to set up a question, but I want to pick up the question rather. Let me pick this one. Okay. What is the probability that a student had A or B, but not both? A student had A or B, but not both. Who can tell us? What is the probability that a student had A or B, but not both? By the way, what does the or here mean? What symbol is that or? A or B, but not both. Please have a book and be writing everything we are saying. If you don't understand, you have to ask so instead of being quiet. A or B, but not both. Both will be A intersection B. A or B is A union B. And A union B is probability of A plus the probability of B. The probability of A is 300 over 3,000. So that is already 0.1. The probability of B is 600 over 6,000. 3,000. Okay. What is that? Do your division in a minute. So you now add the two probabilities, and that will give you. And the reason why you cannot add the intersections is but not both. But not. So when you look at it, that is how you find the basic. These are basics. That's a but not both. These are the basic probabilities that you can find, which is 30% here. So far, so good. You got to understand this classical one is a basic because you're going to deeper ones. So if you don't understand this, say it. Now, there are rules of probability. There are very, very big rules of probability. You see, every game and its rules. The easiest rule is a complement rule. Now, anytime you have a set, like a Venn diagram set like this, the universal set is an omega. An event is a circle like this. Let's call this event event A. Therefore, I can find the probability of A. And that will be everything in the circle. Now, if I want to know everything that is not in the circle, we call it the complement of A. And it's written like this. The complement of A. So the complement of A is everything that is in the universal set, but is not inside A. Like all the spaces in the rectangle, but not inside A. Therefore, if I should add the probability of A to its complement, that should be equal to what? Who can tell us? If I should add the probability of A, write everything down, with its complement, that should be equal to what? The best way to succeed in what we are doing today is to participate, is to ask questions, is to participate, is to ask questions. How would that be? I see that only few people are commenting. Even though there are more people on the call, only few are commenting. You can join the call and then mute yourself. I mean, you can put the sound away whilst you are still able to chat. Okay, that's probably what some of you have to do. Okay. Now, that will be equal to 1. So now let's move on to the real deal. The second rule of probability is additive rule. The additive rule says that A union B, we looked at this already some few minutes ago. The probability of A union B is the probability of A plus the probability of B. That one would never consider the minus part, the intersection. Why? Because in this case, the events are said to be mutually exclusive. Mutually exclusive events or disjoint events are those events that cannot happen at the same time. For example, you being here listening to me, you cannot be at a funeral shaking hands at the same time. It's impossible. Otherwise, that part where you are doing them at the same time makes it joint. So the general case, so mutually exclusive events or disjoint events are where you don't consider the intersection. But when you consider the intersection, which means that you got to take out the joint. Because if you don't take the intersection, you would have done double counting. It is like having a Venn diagram like this, okay, where you have A here, I mean, you have A as this one and then B as this one. And now you talk about A plus B, and you don't take out the one in the intersection because the intersection has also been double counted. So you got to take A intersection B. So A union B will be the probability of A plus the probability of B, but minus the probability of the intersection B. That is the second one. This is the additive rule of probability. There are two of them. One being disjoint, and one being joint. One being mutually exclusive, whereas the other is non-mutually exclusive. Pay attention. Probability requires you to pay attention. Now, I want you to look at this picture very carefully. You've seen it before. I want you to take your mind back to when you were a Kubolo. When you used to like playing games like this. This is a deck of cards. How many cards are in a deck of cards? You can tell us. How many cards are in a deck of cards? How many cards? Class rep, are you here? I really need people to be talking, to be honest with you, chatting or talking. Otherwise, I will fly without realizing. I just wanted to know that. Okay, Miriam says there are 52 cards. Now, those on the first row here, they are known as clubs. We used to call them Kulain, but they are called clubs. Those in the second one here, we call them spades. We used to call them spa. Those on the third row, we call them hats. You got to write these things down. We used to call them yet. And the final bottom one are known as diamonds. And we used to call them what? Who can remind us of the name? Hello. Very good. How many jacks are in the deck?
Say it's lights out here,
so you cannot.
The thing is connected. It says lights out.
So you cannot type, You cannot type in the chat. Is that what you're saying?
Light out.
Are you saying you cannot type in the chat because it's light out? Because I see people on the chat. I see so many of you on the chat. So many. So are you saying that you cannot type in the chat because it's light out? Is that what you're saying? That part, if you are not on the call, that's a different thing. If all of you are not on the call, then I can understand. All right, let's move on. Let's move on. All right, so how many jacks are there? There are 4 jacks. There are 4 queens. And there are 4 kings. Okay. And how many spades are there? There are 13 spades, 13 clubs, 13 diamonds, 13 hearts. Okay, that is how it is. And when you multiply them, you get 52 cards. Keep that in mind whilst we now go through some exercise. Question. From a pack of well-shuffled cards, a card is picked at random out of the 32 cards. Question number 1. What is the probability that the card you selected is a king or a queen? First, you got to ask yourself, how many kings are there? There are 4 kings in all. You ask yourself again, how many queens are there? There are 4 queens. What is the probability that the card selected is a king or a queen? Is a probability of a king or a queen. That is union. You are dealing with addition rule. How do you get this? It is the probability of a king plus the probability of a queen. However, if they are mutually exclusive, then it remains like this. But if they are not mutually exclusive, then it means that you have to subtract the intersection. So let's ask ourselves, king and queen, are they mutually exclusive or they are not mutually exclusive? I know some of you, sometimes the English word for mutually exclusive can be, mutually exclusive means they can happen at the same time. So they cannot happen at the same time. That's mutually exclusive. They cannot occur at the same time. Okay. In other words, you cannot be a king and a queen at the same time. That is mutually exclusive. So my question is, king and queen, are they mutually exclusive or they are not? They are mutually exclusive because it can't be a king or a queen at the same time. It's embedded in the game of a deck of cards. So then what is the probability of getting a king? Remember, there are 4 kings. So you have 4 over 52. What is the probability of getting a queen? There are 4 queens. So you have 4 over 52 cards. You take this and you have your answer. The rest is just using a calculator or using your distance and then finding the best answer to this. And that will give you 2 over 13. That's the first part. The second part is here. What is the probability that the selected card is a king or a diamond? Look at the word, king or a diamond. So let's find something first. Now the word or here means you are still doing what? Union. So you are finding the probability of a king, union, diamond. So first we need to find the probability of a king. Oops. Let's find the probability of a king. And then or means add probability of a diamond. But before we continue, we ask ourselves, king and diamond, are they mutually exclusive or they are not mutually exclusive? Are they mutually exclusive or they are not? Are they ME or not ME? They are, Emmanuel says they are mutually exclusive. And the answer is no. Juliet, what did you have to say?
Doc, please, mine is a question.
Yeah, go ahead.
The mutually exclusive parts, I didn't get it.
Yeah. The only way you can get it is when you translate it into G. It's English. It's when you translate it. 2 things are said to be mutually exclusive if they cannot happen at the same time. Mutually exclusive cannot happen at the same time. Mutually exclusive cannot happen at the same time. You cannot be a boy and at the same time a girl. That is a point. You can't be the same thing. Okay? Non-mutually exclusive means you can be a boy and you can also be a girl. Now, a typical example of a non-mutually exclusive situation is where you are a teacher, but you are also a student. So right now, your profession is you are a worker. You are a worker. But at the same time, you are also a student. Okay, so that is said to be what? Non-mutually exclusive. Okay, but let's say that you are a father and you are also pregnant. These two scenarios are mutually exclusive. They can't happen at the same time. So when two things cannot happen at the same time, that is when we say they are mutually exclusive. In other words, let me use another word. Mutually exclusive events are disjoint, disjoint, disjoint. And non-mutually exclusive events are joint, are joint. They can happen at the same time. So the question you got to ask yourself here is that, can you be a king and at the same time be a diamond? Well, if you have not learned the deck of cards before, it might be confusing. But so let me show you. Look at the kings. Is it possible for a king to also be a diamond? A diamond is the one at the bottom. Do we have a king who is also a diamond? Yes, we do. So it means that you can be a king and at the same time, you can also be a diamond. So when you count the diamonds, they are 13. And when you count the kings, they are 4. But you got to be careful and say that when you put them together, that will be 13 plus 4. No, because one of them, who is a king, one of the diamonds, who is a king, the guy here, has been doubly counted. That is the mutually, non-mutually exclusive part. Okay? And that guy has to be handled separately. So once you identify this, you come to the question, what is the probability that the selected card is a king or a diamond? So let's count. Now we know that a king can also be a diamond. So, and that word can also be a diamond is intersection. And you have to take that out, else you would have done double counting. So you have to take out the probability of king intersecting diamond. Because these two events are joint. These two events of king and diamond are joint. So let's calculate the probability of being a king. There are how many kings? 4 kings. What is the total number of cards? 52. So the probability of being a king is 4 divided by 52. Plus, what is the probability of being a diamond? There are how many diamonds? 13. Out of how many cards? 52. Okay, but we already know that these two events are joint. So let's find out how many of the kings is also a diamond. It's 1. Therefore, you have to take out that 1 out of the 52 cards. This is how you gotta work. And once you're done with that, you sort it. You put them together, find the solution, and that will give you this very answer of 4/3. Okay. What I did is what you just see here. And you will get 4/13. Of course, when you take this 4, 2 goes into 4, okay, you get 2. 2 goes into 52. You can see that. And then you can take this one and then find this and then divide it and subtract it all. You get an easy one. That's like taking the 9. When you have this one will be 8, minus 7, and then you can now go and then do the subtraction. Then you get 4/13. So that is how you find the K union Q. If you don't understand, you cannot. But that's how you get it. Now, these are 2 rules of addition. Let's look at another rule called multiplication. So just note that the additive rule, there are 2 scenarios, joint and disjoint. Let's go to the multiplication rule. Multiplication rule 2, there are 2 scenarios, dependent, independent. Dependent, independent. Remember, multiplication rule means that you are multiplying the event. But how do you know that you are multiplying the event? The nature of the question will give you the clue that you are multiplying the event. Let's take an example. Event A and B are independent. In other words, they don't depend on each other. If the probability of A given B equals the probability of A, so that this is the most important part. The probability of A intersection B is a multiplication of probability of A and probability of B. Watch that word. This word here means both A and B. The word both A and B is an intersection. The word B, A or B is a union. That's what you got to put in your mind. Okay? A or B is union. A and B, or both A and B, is, what is that? Both A and B is intersection. So keep that in mind. Okay? That is a principle. So when you come here, the rule is a rule. The rule says that probability of A intersection B is a probability of A plus the probability of B. Why is it a rule? You can prove these rules. But hey, it's like me telling you 1 plus 1 is 2. Why is 1 plus 1 2? 1 plus 1 is 2. Why is 1 plus 1 2? 1 plus 1 is 2. Let's take an exercise. It will give you an idea. The probability that you get A in statistics is 70%, 0.7. The probability that you will get A in machine learning is 50%. So look at it. These are two difficult subjects. Assuming, you see, now he's giving you the clue. These two subjects are independent. Now you know they are independent. They don't depend on each other. In other words, you don't need to have knowledge of machine learning to be able to understand statistics or the other. Assuming. Find that probability that you will get A in both. So you're being asked to find the probability that you will get A in both. So what is the probability of, the word both means that if statistics is S and machine learning is M, he's asking you to find the intersection of them. And because the two events are independent, then you will use this probability rule, which says that we should find the probability of statistics and multiply that by the probability of machine learning. That will be it. So the probability of statistics is already 0.7, and the probability of machine learning is 0.5. The rest is history. Now, why did we know that we were multiplying? Because we were told that the thing is independent. And you know that independent deals with multiplicative rule. Deals with multiplicative rule. That is why we have to do it like that. Next one. Everything I did is here is 35%. Now, another rule, which is still the second rule, which is not independent, but rather dependent. Okay, dependent or conditional. Okay. Whatever you do is dependent on what I say. Whatever you do is conditional on what I say. It's the same thing. Two events are conditional. If A intersection B is probability of A times the probability of A given B. Now, the intersection, which is the both, it is also true that provided that you are going to find a probability of A intersection B, and that should be equal to the probability of A multiplying the probability of A given B. So first, you must know the probability of A. And second, if B has already occurred, what is now the probability of A? Because they are dependent. They're dependent. Let's take, for example, Man United is playing Chelsea. Man United scores the first goal. Okay, that becomes the probability of A, Man United scoring. Then Chelsea scored 2. So now Man United is down by 2-1. Now, Man United goes and scores a second goal. Now, that second goal may be as a result of the goal that Chelsea scored them double. And that heated them up and that elevated their gymnastics. And so they were now ready to do something. So that second goal they are scoring is conditional, is dependent on the two goals that Chelsea has scored. So even though you are finding the probability of A, the next one is the probability of A, given that Chelsea has already scored you. So the way you treated the first goal you scored, it wasn't as much with energy than the second goal. This is conditional probability. Let me give you a story. Two cards. You pick them in succession, one after the other from a card. There are 52 cards in a deck of cards. You close your eyes. You pick one card. After every draw, you don't replace the card. So if there are 52 cards and you pick the first one and you don't replace the card, how many cards are in the card now? How many cards are now left? Type it there. Without replacement, so how many cards are now there? You have 51 left. Be with me and be answering it, typing the answer so quickly. Okay? So there are 51 cards left. What is the probability that in both the first and the second draw, you will get spade? What is the probability that you get spade in both the first and the second draw? Well, you know that the second draw, you see, this is knowledge. You think and you come to realize that the second draw will be dependent on the first draw. Why? There's dependency here. And the reason why there's dependency is because by the time you do the second draw, the number of the cards which were in the first draw have reduced. So the probability is as a result of the first event happening. That is why you see the probability of A multiplying the probability of A, giving that something has already happened. Now, let's try and find the first situation. So let's say that the first one, let's call it F. So the probability of collecting the first card of spade. And then you are now going to have the probability of getting, what do you call it? The probability of getting the second card, which is given that the first card has already happened. Okay, that's what you're doing. You're multiplying. So let's try and find out, what do you think is going to be the probability of getting a spade? The probability of getting a spade. How many spades are there? What will be the probability of getting a spade? There are 13 spades. You remember that? That's 52. The second scenario. Now that you've taken, in the second situation, there are no longer 52, and you're now going to pick a spade again. So this time you have 12 and 51. This second one is contingent on the first one. And now you can calculate that, okay? This is it, by the way. You can calculate that and you get this value down here. Yeah, I'm getting the intersection. That is the both. Both of them are happening. That is going to be 1/17 when you multiply. So this is said to be the dependent rule of multiplication. So we've only looked at two rules. Now, well, three rules. The first is a complement rule. That one is just easy. The second is additive rule, and there are two elements of it, whether it's mutually exclusive or non-mutually exclusive. Then the third one is a multiplication rule. There are also two stories, whether it's dependent or independent. The other ones I'm not going to teach you those ones. Learn them if you can. One of them is called a conditional probability. And the other is known as the Bayesian statistics or Bayesian theory. Thomas Bayes in the 1700s developed a powerful rule of probability based on the conditional probability here. And that rule became the Bayesian rule. It's a beautiful rule, but it's a little bit complex. I'm not going to bore you much on that. Now, let's go to the topic, the real topic of probability for today. Random variables. Guys, I want you to look at the height of some people. One of them is 5.6 inches. One of them is 5.7. One of them is 6 inches. One of them is 6.1. Then maybe another one is 4.9, very short. These are numbers, a series of numbers. Now, in this series of numbers, anything is possible. I can put all these series of numbers together and represent it as a random variable, x. Now, because the numbers are decimals, it is not going to be a mere random variable. It's going to be a continuous random variable because it involves measurement. But if the x are 1, 4, 6, 9, these are whole numbers, then it becomes a discrete random variable. These are integers, counting numbers. But there are certain things in life that are already whole numbers. And there are certain things in life that are already decimals. For example, I just told you about height. Height will always be decimals. Age will always be decimal. You can never be 5 years old alone, 6 years older. You can be 5.5 years. You can be 5 years, 7 months. You can be, they are decimals already. So what is not decimals? Automatically. Well, take something like sex type. You are either a boy or a girl. It's decimal. I mean, it's a whole number. And not just that, there are other things that are whole numbers as well. For example, we spoke about the number of cars. The number of cars is always going to be whole numbers. 1, 2, 3, 4, 5. So a random variable is a series of whether it is a whole number or it's a decimal number. If it is a discrete number, you have the direction like that. They are in bits, 1, oh, you see, they are standing on their own. That is whole number. But because this one is decimals, they have a smooth kind of bell-shaped curve because any slight little points is possible. That's what we mean by a random variable. Keep that in mind because we are going to build on that. That's the first thing. The second thing is the probability distribution of the random variable. I've already told you. You see, I gave you numbers. As you stretch the numbers, you can see how they look like. The way they look like, the way the series of the numbers look like is what we mean by the distribution of the numbers. So the distribution of a random variable, okay, or the probability distribution of the random describe the look of the random. How does it look? For discrete random variables, those that are whole numbers, there are 2 of them we are going to look at. For the continuous random variable, there's one we shall look at next time. Let's start with the random variable that are whole numbers, the discrete. We are going to look at the first one. And this first one is known as a binomial distribution. The word bi comes from the word 2. A binomial distribution is a Bernoulli trial. A Bernoulli trial is a random experiment where the outcome is only 2. Now watch the word. It's a trial. It's one trial. It's a single trial, Bernoulli. But when the trials are many, it's no longer Bernoulli, it's binomial. So what is the difference between a Bernoulli trial and a binomial trial? A binomial trial is multiple trials. A Bernoulli trial is one trial. Now, what do I mean by a trial? You know, when the footballers are about to play football, the referee will take a coin and will throw the coin into the air, palm, and show whether it is a head or a tail. That throwing that coin into the air and catching it with the hand and showing the head or tail, that process is a trial. Suppose the captain of one of the team is not happy with what the referee did. No, I don't like the way you did the throw. Do it again. Now we have a second trial. It's no longer a Bernoulli, it's binomial now. But what is the outcome here? The outcome is still going to be a head or a tail. So the binomial is a binomial distribution is a distribution where the outcome is a success or a failure. Please, I want you to note that the success or the failure I'm talking about doesn't mean good or bad. There be no. The success is good and the failure is bad. No. The success can be the head. The failure can be the tail. There is nothing bad about a head. There is nothing good about a tail. There is nothing good about a tail. There is not, so do not attach morality to the success word, the word success or the word failure. For example, there's going to be an election. There could be chaos, which is a success, or there could be calmness, which is a failure. You see, chaos is being represented as a success. It doesn't mean that chaos is good. So I do not want you to attach immorality to the word success or failure. But the key point you got to understand about binomial is that the outcome is just 2. The experiment or the trial is made up of sequence of series of trials. And that takes move from Bernoulli to binomial. But there's one characteristic you got to know. The probability of the success will not change. It has to be what it is all the time. For example, if I throw a coin into the air, the probability of getting a head is what? Who can tell me? If you throw a coin into the sky, the probability of getting a head is what number? Half. Very good. Most of you are saying half. It's half. It's 50-50. It's 50-50. You can get a head, you can get a tail. And if I throw it again, that probability of getting a half will not change. If I throw it 100 times, the probability will still remain the same. So one characteristic of a binomial or Bernoulli trial is that the probability of the success, what you are looking for, is always going to be the same. Finally, the trials are independent. The second trial should not be dependent on the first trial. Neither does the third should be. So the way you threw the thing, now, the way you threw the thing, you threw it this way, so it worked. So the next time when I throw it this way, it will work. Like, no, it should be independent. There is no skill. There should be no skill of throwing the thing for it to get it. The chances are 50-50. That's the point. Now, what is our goal here? Our goal is to model the number of successes occurring in a trial. Before you can ever use a binomial, this is what you should do. Know the examples of binomial distribution. And because I've been talking a lot about the head or tail, I've given you one example. Can you give me another example of a situation, events, experiments that are binomially distributed? Don't give me sex, which is male or female. Can you give me another example apart from sex or female? Apart from male or female, can you give me one example? I need more answers. Oh. I need more answers. A card being black or red? No, because the possibilities are the colors of the world are not black or red. They are multiple, so you can't. The outcomes must be just two, not many. Yes or no is ideal. Yes or no is ideal because the outcome of yes or no is always going to be two most of the time. So that is an acceptable one. What else? Apart from yes or no. True or false? Very good. Win or lose? Very good. Excellent, Abigail. Excellent, Nana. Excellent, Reginald. Can be, yeah, can be known. What are the other possibilities? Think about other possibilities. Usman, somebody has already said yes or no. Okay. So you can have defective or non-defective light bulbs. You can have defective or non-defective. You can have yes or no. You can have accept or reject. All of these are possibilities. Okay, now I want you to write the formula for the binomial down. Please write it down. This is the formula for the binomial. Write it down, please. Yeah, get to tall or short is quite difficult because there's a lot of ranges in between. There's a lot. Medium, short, medium, tall, and all of that. So it's quite difficult. When there are possibilities of ranges in between, it cannot be binomial. Write this formula down. And we're going to talk about it. Please write this formula down. Please write it down in your book. Please write it. All right. What does the exclamation mark mean? Who can tell me? The exclamation mark, what does it mean? Factorial, very good. We'll come and talk about it very soon. What does the N mean? The N. The N stands for the sample size. The P stands for what? Probability. The X stands for what? The number of successes out of that series of success. So the N is a series of success, and then out of that sample, X is this. And the N is the trials out of that sample, X is the number of successes. Please note that 0 factorial is always equal to 1. What is 1 factorial? Who can tell us? What is 1 factorial? What is 1 factorial?
1.
1. You must know this in your calculator because you gotta see all of them on your calculator. That's the way you can solve it. Okay, so now we're going to look at scenarios, multiple scenarios about binomial and when to use it. The moment you know the binomial distribution, there are 2 things you got to know about every distribution. 2 things. 1, you got to know the mean and the variance. The mean is also called expected value. Please write this two formulae. The expected value or the mean of a binomial distribution is the sample multiplied by the probability. That's it, write it down. And the variance is the sample multiplied by the probability of success multiplied by the probability of failure. The probability of failure is the 1 minus P. The probability of success is the P. The probability of failure is the 1 minus the P. And please remember that the square root of the variance is equal to what? You can tell us. The square root of the variance is the standard deviation of Ebenezer. That's excellent. Guys, if you didn't know, Ebenezer has given you the answer. The square root of the variance is the standard deviation. Sometimes you'll not be told to find the variance, you'll be told to find the standard deviation. Well, all you got to do is to just find the square root of what you have. Let's move on. So that is the first distribution. The second distribution we are going to discuss is the Poisson distribution, not Poisson, but Poisson distribution. A Poisson distribution is very, very similar to the binomial, but also very different. The focus is to find the number of events, and here's a word, over a continuous interval. The continuous interval here can be interval of time, from this time to this time. That's one. Another interval can be space, from this distance to this distance. Another interval can be length, or it can be an area. But the key point is that because you have from a point of interval to a point of interval, what you can now talk about is not the exact success, but you can talk about the mean of the success. So it is a discrete random variable, just like the binomial, for count. So they are still whole numbers. It is a limiting case of the binomial. But a good important thing you should know about a Poisson versus the binomial, and this is the most important thing for today, because if you don't know the difference, you will get stuck. And I'm going to give you a way to catch the difference. You see, when you talk about a Poisson, the mean of the event is the focus. The mean of the event within the interval, whether the interval is space, is time, it's a page, it's a distance, it's a something. Interval is not only about time. It can also be about space. It can be a space on a paper, a space on a laptop, a space on a wall, a gap from here to here. And that from here to here interval is what creates the mean. In that case, the Poisson is used. But if the exact probability of the event is given or is implied, if you don't need the mean, you just need exact probability, you just need the absolute number, not an interval of numbers, then the binomial is used. I'm about to ask you a series of questions here. I have some statements here. Your job is to tell me whether it's binomial or Poisson. I have mixed them. Yours is to tell me whether it's binomial or Poisson. But before we do that, let's write a Poisson formula. Oh, let's look at the examples first before we write a Poisson formula. The Poisson formulas, the examples. So look at the first bullet. Tell me whether it's binomial or Poisson. Be careful. The first one. If it is binomial, type B. If it is Poisson, type P. The number of arrivals in a shop in 1 hour. Is that binomial or is Poisson? Choose only one option. Don't change it. Only one. Okay. Most of you are saying Poisson, 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 Poisson. That's correct. Why? Because it is within an hour. Very good. Let's go to the next one. The goal scored in a football match. Binomial or Poisson? The goals. Binomial or Poisson? I need answers. I've typed the word goals because I want it to be differentiated from the previous answers. Be careful. Is this binomial or Poisson? Ubisimin can be. Sawara. Okay, so only one of you have gotten it wrong. It is Poisson. Why is it Poisson? Why is it not binomial? Who can tell me? I need a voice now. Why is it not binomial, but it's Poisson? Why? Why do you think so? It is Poisson because the goals are scored within 90 minutes. Within interval, 90 minutes. Just that it wasn't mentioned, but you should deduce it. It happens within 90 minutes. If I said goals scored in a football match, a 90-minute football match, you would have gotten the clue. Next one. Imperfections per square meter of a glass panel used to make LCD TV. Imperfections used to make LCD TVs. Binomial or Poisson? It is Poisson. It's clear. Next one. Robot malfunctions per day on an assembly line. Robot malfunctions a day on an assembly line. Let me type robot so that it doesn't confuse with the others. Is it binomial or Poisson? Binomial or Poisson? It's Poisson. It's Poisson. Flaws on the length of a cable. Be careful. Flaws on the length of a cable. Is it binomial or Poisson? Is it bi or Poisson? Bi or Poisson? Flaws on a cable. It's Poisson. Getting or not getting a bidding contract. Binomial or Poisson? Binomial or Poisson? Getting or not getting a contract. It's binomial. Excellent. So with that, you have learned, though, when we get to the practicals, we'll see you have learned. Now write the binomial formula. Please write it down, just like you got that of the other. Write a binomial formula. If you look at the formula of binomial carefully, it is exponent. Okay? The E here is talking about the base of the natural log. The value of this is always 2.718. It's down here. Always 2.71. The lambda is the mean of the event. I told you that Poisson deals always with the mean of the event, not the event, but the mean of the event. The X is always the probability of the success, but within that time frame, given the interval. So the only two things you need for the Poisson is 2. But the things you need for the binomial is 4. And you're going to see that. Please write the formula down. Now we're going to solve real-life questions, mixing binomial and Poisson. Yours is to identify whether it's binomial or Poisson before you solve it. Because if your identification is not correct, your solution is wrong. Please, I want all of you to participate in what we're about to do. It will help you to raise your mental gymnastics to the highest apogee. Are you ready? If you're ready, type yes. Oh, but hold on. Before you're ready, let me give you the mean and then the variance for Poisson. The mean and the variance for Poisson are always the same. The mean is a lambda. The lambda is a mean. And then the standard deviation, the variance is also the lambda. So keep note. The mean and the lambda, the mean and the variance are always the same for Poisson. It's not like that for the binomial. Binomial, if you can remember, the mean is NP. N is a sample size, P is a probability of success. And then the variance is NP 1 minus P. So that is the sample size multiplied by the probability of success multiplied by the probability of failure. They are different. But a Poisson, the mean is the expected value, or the mean is a lambda, and which is the mean, and the variance is also lambda, which is also the mean. If you are ready for the exercise, let's start. First question. What is the probability of one success in 5 observations if the probability of success is 0.1? All I need from you is this. Tell me, is this binomial or Poisson? What's the first one? Is this binomial or Poisson? Type it there. B or P, without copying it from anybody. Everybody type something. Binomial or Poisson? Bi or Pois? The first person says by, the next say Poisson, by, Poisson, Poisson, by. Say some. Say some, you won't die. Okay. So this is binomial. What is a key word that helped you to know that it was binomial? Can tell us a key word. One word, not two, one. What is that one word that give you the clue that this is binomial? It is a word success, correct. Once you have a success, you have a failure. So this was quite obvious. Now that you've identified that, the next thing now is to identify the element of the formula. The formula requires you to have x, p, 1 minus p. Sorry, it requires you to have n, p, 1 minus p, finally x. So we look through carefully and ask ourselves, what is the sample size here? You have to identify this first before you put it into the formula. What is the sample size here? Correct, it's 5. What is the p here? What is the probability of success here? Correct, it is 0.1. Master, you're doing really well. I love people who show clear collaboration, clear participation. People like that, there's no way when they're even struggling, I will not pass them. All right, now you have 1 minus p. What is that value? What is 1 minus p? 0.9. And then x is what the question will normally ask you. So what is the x? What is the x? X value is what? What is the x? The x is a 1 success. So it's 1. X is 1. You see, if some of them have been written as actual numbers, you would have detected it easy. So now that you have this, you have to put it into the binomial formula. And we already know the binomial formula. This is a binomial formula. So substitute these into your binomial formula and tell me your answer. If you are able to tell me your answer, you may face a problem. And it's better you work it and face a problem. So I tell you why. Than you don't work it, you don't face a problem, and you face a problem rather in the exam. So please solve it and tell me the answer you got for this. I'm waiting. Send me your answer privately. All right. So I got only two answers. Only two answers from some remarkable people. Very good. So you are going to have this answer if you work it well. You take a calculator and work it, you're going to get 0.32805. 0.32805. So it means that the chances of getting 1 out of the 5 is 32% or 33%. Okay. Now, let's go to the next one. What is the probability of getting exactly 2 tails in 3 tosses of a coin? My interest now is not to be solving most of these things, but also more of identifying whether it's binomial or Poisson. Because once you know it's binomial or Poisson, all you got to do is to just substitute them into the formula. And more importantly, your identification of the numbers and the writing where the sign you got to put for the X variable. The first one that we did, X was not greater than 1. No, this was not the case. X was not less than 1. No. X was not less or equal to, no. X was not greater or equal to 1, no. X was equal to 1. That was the first one. Let's go to the next one. So this next one, you have, what is the probability of getting exactly 2 tails, 3 tosses of coin? Is this binomial or Poisson? This one here, is this binomial or Poisson? Is this binomial or Poisson? Bi or Poisson? It's binomial. Very good, Prince. So this is binomial because of the word coin. Anytime we are dealing with a coin, it is binomial. Okay. The fact that you have 2 in 3 tosses doesn't mean that, is the mean. No. Now that you have identified that is binomial, binomial has got 4 elements. You have the n, you have the p, you have the 1 minus p, and s. What is the n here? What is the n? 3. Very good. What is a p? The probability of success. Because it's a coin throw, we know that it's going to be automatically 0.5. What is a 1 minus p? Because it's a coin throw, it's going to be exactly 0.5. And what is the x? He made it very clear. The word exactly means equal to. So x is equal to 2. Finish. Once you know that this is the case, you just substitute them into the binomial formula like this. Then you get the answer to be 37.5%. That is how you calculate it. Remember, x is 2. So that is why we substituted it. Wherever we see x in the formula, substituted it 2. Now, let's go to another example. Samsung Ghana gives a 2-year warranty on the phones it makes. This is practical. From past experience, it knows that 0.5% of these phones will be faulty and fail within the warranty period. What is the probability that out of a consignment of 500 phones, none will be faulty? More than 3 will be faulty. Is this binomial or Poisson? Is it binomial or Poisson? This is a most important part to me. That's why I delay normally here. Binomial, correct. Prince, you're doing very well. Why is this binomial? It is not binomial. I tried. You said something. This is not binomial. Why is it not binomial? Because of the word 2-year warranty. Whatever that is going to happen is within the 2-year warrant. So there's a time interval. And that should give you the clue that this is Poisson. Now, your ability to determine that this is Poisson in the first place is the first yardstick to proceed. Now that you know it's Poisson, Poisson only needs two things, the lambda, which is the mean, and then the x, which would normally come from the question. The first part of the question, it says that none will be faulty. It didn't say at least none will be faulty, or at most none will be faulty, or no more than none will be faulty. It says none will be faulty. So that means that x is equal to none, 0. What about the mean? Oh, there was a lot of confusion a bit about the mean. It says that from past experience, it knows that 0.5% of the phones, 0.5% of the phones. How many are the phones? 500. And it says from past experience, that is over a period. So now that's the mean. So it tells you that to get the mean, you need to multiply the 0.5%. Remember, it's 0.5 over 100, 0.5%. Multiplying the 500. That will give you the average of the phones that get faulty. That will give you the mean faulty phones. This will be equal to. So with a mean of 2.5 and the x of 0, so what's the probability that none, 0, will be faulty? That's what you're about to find. Substitute that. Let's go and check. So first thing you got to do is to write your binomial formula, okay, like this. Substitute. This is a probability that x is 0. Okay. This e is the base of the natural log, which is 2.718. Just write that. The lambda is negative 2. Lambda is 2, but then the formula says you should have a negative. So you have 2.5 raised to the power 0 for this. Divide that by the 0 factorial. That will give you 8.2%. So the chances of getting no phone being faulty is quite slim. The chances are 8.2% chance. But there's another part to the question. What is the probability that out of that number, 500, more than 3 will be faulty? You see, at this stage, he's telling you that x has something related to 3. What symbol will come in between them? What symbol is that? So we're looking for the probability that x is something related to 3. What symbol is that? It will be greater than. Greater than. Very good. Very good, Maxwell. You didn't say less or equal to. Okay. This is more than 3. So that's more than 3. Okay. More than 3. But look at it. The phones are many. There are 500 phones. So if you want to do more than 3, then it means you're going to do 4, 5, 6, 7, 8, 9, 10, 11, 12, up to 500. By the time you finish, your grandchildren are married and gone. So there is a principle in probability you will use. Because we know that at the end of the day, the total probability should be 1. So another way of writing this is this. You can say that 1 minus the probability that this time x is less or equal to 3. Because remember, the first one is more than 3. So the opposite of that will be 3 or less. So that is what you should rather find. So it means that we need to go and find 1. We should find what are the things less than 3. We should find probability that x is equal to 0, which you already have from the previous question. You should add that to the probability that x is equal to 1. Add that to the probability that x is equal to 2. Add that to the probability that x is equal to 3. Whatever you get, subtract it from 1. And that will give you the more than 3 output. So you don't need to do all the way from 4 to 500. You just need to take 1 minus the probability of the rest. And that is what you got to do. So let me show you. So when you do that, you're going to DC. So you have the probability of 0, you take a probability of 1, probability of 2, probability of 3. And then once you get these probabilities, what do? You take each one of them from 1, or you sum them all and subtract from 1. And that will give you 24.2%. So it means that the chances of you getting more than 3 funds being faulty is 24%. So learn how to be able to use that 1 minus principle to always address probability issues. This is another one, another easy peasy one. Bob is concerned about a low retention rate of employees. Management has seen turnover of 10% of the hourly employees annually. Therefore, for any hourly employee chosen at random, management estimate a probability of 10% that the person will not be with the company next year. Choosing 3 hourly employees at random, what is the probability that one of them will leave the company? There's a principle here, which is the word leave. So there's a choice here, leaving. Okay, leave. Then it says that in recent years, management has seen a turnover of 10% of the employees annually. That turnover means that some of them are leaving, okay, which means some of them are also staying. And then it talks about the probability that a person will not be with the company next year. That is, will leave. So what is this? Is this binomial or Poisson? I'm sure you get a principle, right? Is this binomial or Poisson? Let me see. Abigail says it's Poisson. Ebenezer says it's binomial. Miriam says it's Poisson. Oh, hey, I didn't think there was going to be a lot of this thing. If you look at it very carefully, you will know. You will know exactly which one it is. And it is binomial. Okay. The reason why it's binomial, I just gave you an principle of leave, which means if you are either leaving or not leaving, either leaving or not leaving. That's what it is. So this was a clear binomial. And then the probability of success was 10%. It was given. N was 3. And then 1. You can see that 1 from here. What's the probability that 1 out of the 3? So that is how you address this one. And then, of course, the latter part says find the mean and find the standard deviation. Well, that's fairly simple. The mean is the n times the probability. N is 3. The probability is 0.1. So the mean will be 0.3. The variance of x is that n times the p times the 1 minus p. So that will be 3 times 0.1 times 0.9, which is all here. Okay. 3 times 0.1 times 0.9. That will give you 27%. That's the variance. And you can also find the standard deviation by taking the square root of this variance. You see, at this stage, I'm expecting that the calculation is not my issue now. My issue now is you understanding when it is binomial and when it is Poisson. Let's look at the last part too. In a typical month, an insurance agent presents life insurance plans to 40 customers. Historically, 1 in 4 chooses to buy life insurance from the agent. Based on this, calculate all this. Is this binomial or Poisson? And what word or words guide you? Is this binomial or Poisson? Bi or Poisson? Bi or Poisson? I need answers. Maxwell has given me his answer. Is it bi or Poisson? This is very tricky. If you don't take it, you might think it's Poisson, but it's not Poisson because that typical month was not specifically given. A month can be 30 days, a month can be 31 days, a month can be 28 days. So it wasn't specific for you to know the interval. But what guides you here is this chooses to buy, because that was the guide. historically, 1 out of 4 customers chooses to buy life insurance or chooses not to buy. So there is a binomial treatment here. Chooses to buy or not to buy. That is why towards the end, it says, what is the probability that exactly 5 will buy from this agent? So it's not that month that you use to guide you. Okay. Because if you choose that as the month, then what will be your mean? If you choose this one, what will be your mean? Because this is not the mean, because this is 40 customers. So that will not be the mean. Okay. And if this is the mean, anyway, so the key point is that the month is not specific enough. You can't just say, you see, if you say a week, it's clear because a week, all weeks are 7 days, but all months are not 30 days. So take note of that. So this is a pure binomial. Okay. Exactly 5 means that P is equal to 5. And so that is what you have here. P is equal to 5. And then you can calculate the binomial. Okay. What is the probability that no more than 10? No more than 10 is greater, less or equal to 10. So you have to solve from 0 all the way up to 10. Okay. And then here, he was asking you about the mean. Instead of asking you the variance, it will also ask you the standard deviation, which is okay, because the standard deviation is just the square root of the variance. What is the mean? The mean is the sample size times the P, which is a probability. What was the probability here? Look at it. 1 out of 4 customers chooses to buy. That's a probability. So 1/4, which is 25%. 1 out of 4 chooses to buy. So that is historically. That is what has been happening historically. That becomes the probability. Okay, so that was a little bit tricky. Once you have this, you can now find the final ones. Okay, let's look at the very last one for today. Hisense Ghana produces and sells TVs. The TVs are inspected at the end of the production process at a quality control station. Out of every batch of TV, 4 are randomly selected and tested for defects. Given that 20% of the batches are defective, what is the probability that each batch will contain exactly 2 defective TVs? Is this binomial or Poisson? Bi or Poisson? You should get this, because once you miss this, it means that you have a lot to go and prepare for that. It is binomial, and you're all getting it correct, okay? You're all getting it correctly. Okay, so that one is cool. There's no hard and fast rule about it. That one is cool. The rest is just history. So, ladies and gentlemen, that is how you handle binomial and Poisson analysis. Next time, we shall look at the mother of all distributions, and that is known as the normal distribution. We shall look at that, and then if you have some further questions, you can. But as of now, if you have any question, please, this is a time. You can come closer and you can ask your question.